What if I told you that you are standing at the center of the observable universe right now, and that so is every alien civilization, every distant galaxy, and every observer anywhere in the cosmos? It sounds impossible. If everyone can claim to be at the center, then perhaps the word center has lost its meaning. Yet this is exactly what modern cosmology forces us to confront. The universe is expanding. Galaxies are racing away from us in almost every direction. The farther they are, the faster they appear to recede. At first glance, that seems to place us in a privileged location, as though the entire cosmos were exploding outward from somewhere near the Milky Way. But physics says something far stranger. The expansion has no known central point in space. The Big Bang did not happen at one location. It happened everywhere. And once you truly understand what that means, the familiar picture of the universe begins to collapse. For most of human history, the center of the universe seemed obvious. It was here. Ancient observers watched the sun, moon, planets, and stars sweep across the sky, apparently circling Earth. Aristotle built a cosmos of nested celestial spheres around us. Ptolemy transformed that picture into an elaborate mathematical system. Earth sat motionless at the center while the heavens moved around it. Then came one of the greatest humiliations in intellectual history. Copernicus displaced Earth from the center. Galileo revealed worlds orbiting Jupiter. Kepler replaced perfect circles with ellipses. Newton showed that the same law pulling an apple toward Earth also controlled the moon and planets. The universe was no longer divided into a special earthly realm and a perfect celestial realm. But humanity still had room to retreat. Perhaps Earth was not central, but maybe the sun was. Then astronomers discovered that the sun is only one star among hundreds of billions in the Milky Way. Perhaps the Milky Way was central. Then Edwin Hubble and others helped establish that many faint nebulae were actually galaxies far beyond our own. Every time we searched for a privileged cosmic position, nature seemed to erase it. But then astronomers found something that looked disturbingly like a return to the old idea. In the 1920s, observations showed that distant galaxies were overwhelmingly redshifted. Their light had been stretched toward longer wavelengths. More importantly, the farther away a galaxy was, the faster it seemed to be receding. Imagine standing in a field while thousands of lights rush away from you. Nearby lights move slowly. Distant ones move faster. What would you conclude? The obvious answer is that you are standing near the center of an explosion. That interpretation would be reasonable if galaxies were pieces of debris flying through pre-existing empty space from a single blast point. But that is not what the standard cosmological picture says. The deeper description comes from Einstein's general theory of relativity, the theory that transformed gravity from a force into geometry. Space and time are not a rigid stage upon which matter moves. They are dynamical. Matter and energy influence the geometry of space-time, and that geometry influences how matter moves. Once space-time itself becomes dynamical, something extraordinary becomes possible. Space can expand. This distinction is the key to the mystery. Galaxies are not simply flying outward through static space from one central point. On very large scales, the distance between sufficiently separated, gravitationally unbound galaxies grows because the geometry describing the universe changes with time. Leonard Susskind has spent much of his career working in exactly the kind of physics where our everyday intuitions about space become unreliable. From black holes and quantum information to string theory, holography, and cosmology, Susskind's work repeatedly confronts the idea that space may not be as fundamental as it appears. And the expanding universe gives us one of the cleanest examples of why intuition can fail. Picture an enormous sheet covered in evenly spaced dots. Now imagine stretching the sheet uniformly in every direction. Every dot sees every other dot moving away. A dot does not need to be at the center of the stretching. From any chosen dot, more distant dots separate faster because there is more stretching space between them. There is a problem with this analogy, of course. A physical sheet has edges, and it exists inside a larger space. The universe does not need either of those things. The analogy is useful only for understanding how distances can increase without requiring a special central location. The famous balloon analogy tries to go one step further. Imagine galaxies drawn as dots on the two-dimensional surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot along the surface. A tiny creature confined entirely to that surface could search forever for the center of expansion and never find it. The balloon does have a center, but that center lies outside the two-dimensional surface the creature inhabits. This is where people often make the wrong leap. The analogy does not mean our three-dimensional universe must be the surface of some four-dimensional cosmic balloon with a physical center hiding in another dimension. The extra dimension is part of the visualization, not a necessary feature of standard cosmology. The real point is simpler and more unsettling. A space can expand intrinsically. It does not have to expand into something. That idea becomes even more important when we ask where the Big Bang happened. If you rewind the expansion, distant galaxies become closer together. Rewind far enough and the universe becomes hotter, denser, and more uniform. Continue toward the earliest times described by our current models, and the scale separating regions shrinks dramatically. The tempting image is a tiny fireball located somewhere in darkness. Then the fireball explodes. But that image is wrong. The Big Bang was not an explosion of matter from one point into surrounding empty space. It was an early, hot, dense state of the universe itself. Every region of the observable cosmos traces its history back toward that state. The galaxy 10 billion light-years away did not emerge from a cosmic explosion point and travel outward until it reached its present location. The region of space in which that galaxy formed was also part of the expanding universe. So was our region. So was every other region we can observe. This leads to one of cosmology's strangest statements. The Big Bang happened everywhere. Not everywhere in the sense that countless separate explosions occurred, but everywhere in the sense that every present-day region was once part of a much hotter and denser cosmic state. There was no empty outside into which the Big Bang expanded. At least none is required by the standard theory. And yet another paradox immediately appears. If there is no center, why does the universe look centered on us? Look outward in any direction, and you see deeper into cosmic history. Because light travels at a finite speed, distant objects are seen as they were in the past. Eventually, we encounter the cosmic microwave background, ancient radiation released when the universe became transparent roughly 380,000 years after the beginning of the hot Big Bang era. That radiation surrounds us in every direction. So we appear to sit at the center of a vast, spherical, observable universe. This sounds suspiciously like the ancient picture all over again. But imagine an astronomer living in a galaxy billions of light years away. That observer would also see a spherical observable universe centered on their own location. Their cosmic horizon would differ from ours. Some regions visible to us might lie beyond their observable boundary, while some regions visible to them could be inaccessible to us. The center of the observable universe is therefore not the center of the entire universe. It is simply the location of the observer. You are at the center of what you can observe because information reaches you from all directions. A sailor on a perfectly calm ocean may see a circular horizon centered on the ship. Moving the ship moves the visible horizon. No one would conclude that the ship has discovered the geographical center of the ocean. Our cosmic horizon works according to a far deeper geometry, but the conceptual lesson is similar. And now the mystery gets sharper. How do scientists know that we are not secretly near some real center after all? They do not prove the absence of a center by traveling across the entire universe. We cannot do that. Instead, cosmology builds models from observations and asks which geometry best describes what we see. On very large scales, the universe appears approximately homogeneous and isotropic. Homogeneous means that, averaged over enormous distances, no location appears fundamentally unique. Isotropic means that, again on large scales, the universe looks approximately similar in every direction. Locally, of course, the universe is wildly uneven. You are standing on a planet. Nearby is a star. Beyond that are mostly empty interstellar regions, galaxies, clusters, filaments, and gigantic cosmic voids. But zoom out far enough and the large-scale distribution becomes statistically smoother. This assumption that there is no privileged cosmic location or direction is known as the cosmological principle. It is not a mystical rule. It is an approximation supported by observations, including the extraordinary large-scale uniformity of the cosmic microwave background and surveys of matter across the universe. When Einstein's equations are applied to a universe with this large-scale symmetry, They lead to the family of expanding or contracting cosmological models associated with Friedman, Lemaitre, Robertson, and Walker. And in these models, expansion does not require a spatial center. But there is an important subtlety. The universe does contain local motions. Our solar system moves within the Milky Way. The Milky Way moves relative to nearby galaxies. Our local group moves through the larger cosmic environment. And observations of the cosmic microwave background reveal a dipole pattern caused largely by our motion relative to the frame in which that ancient radiation is most nearly isotropic. Does that frame define the center? No. It defines a useful state of motion. There is a difference between having a preferred cosmological rest frame and having a preferred position. Imagine a perfectly straight road covered with cars. There may be one speed at which the average traffic appears balanced ahead and behind you. That does not tell you that your location is the center of the road. Likewise, cosmology can define observers who move with the average cosmic expansion without selecting one special point as the origin of everything. This is the kind of distinction that theoretical physics demands. Velocity is not position, perspective is not privilege, and an observable horizon is not a cosmic wall. But even if the universe has no center, does it have an edge? That question sounds similar, but it is completely different. We do not currently know the full global size or topology of the universe. The observable universe is finite because the cosmos has a finite age and light travels at a finite speed. There are regions from which light has not had time to reach us. But the entire universe may extend far beyond what we can observe. It could be spatially infinite, or it could be finite without having a boundary. That second possibility seems almost impossible until geometry rescues us again. The surface of Earth is finite but has no edge. You could travel around it indefinitely without falling off a boundary. A three-dimensional space can, in principle, possess analogous global properties, although we cannot visualize them as easily. Cosmological observations indicate that space is extremely close to geometrically flat on large scales. But flat does not automatically mean infinite. Certain finite topologies can also be locally flat. This remains an area where observation constrains the possibilities without yet giving us a complete picture of the universe beyond our horizon. And here the question of a center becomes even stranger. An infinite homogeneous universe has no central location. A finite closed universe also need not have a center within its own space. So asking where is the middle of the universe may be like asking where is the starting point of a circle. The question assumes a structure nature may not possess. Susskind's work pushes this discomfort further, because modern theoretical physics repeatedly suggests that spacetime may not be the final layer of reality. One of the most dramatic clues came from black holes. Black holes once appeared to destroy information. Throw a book, a computer, or an astronaut into a black hole, and, according to a naive reading of classical physics, the detailed information describing that object seemed doomed. Stephen Hawking's discovery that black holes can radiate made the puzzle worse. If the black hole eventually evaporates into featureless thermal radiation, what happens to the information? Susskind became one of the leading defenders of the idea that quantum mechanics does not permit information to be fundamentally destroyed. His arguments contributed to the development of black hole complementarity and to the broader holographic viewpoint, the astonishing possibility that information describing a region of space may be encoded in a lower dimensional way. The holographic principle is not simply a claim that our universe is a computer simulation. That popular interpretation goes far beyond what the physics establishes. The deeper idea is that the number of fundamental degrees of freedom required to describe a gravitational region may scale in an unexpected way, tied to boundary area rather than ordinary volume. In certain theoretical settings, especially through gauge gravity dualities inspired by string theory, space-time geometry can be related to a lower dimensional quantum description. And that raises a question far more radical than whether the universe has a center. What if space itself is emergent? If spatial geometry arises from deeper quantum relationships, then searching for the center of the universe at the deepest level might be like searching for the center of a melody. A melody has structure. It has relationships. It unfolds in time. But its essence is not found at one privileged note. This is not an established description of our actual cosmological universe. The emergence of spacetime remains an active field of theoretical research, and extending holographic ideas to realistic cosmology is difficult. But Susskind's career illustrates a recurring lesson. Concepts that seem fundamental can turn out to be approximate. Position, distance, inside and outside, even space. The universe without a center is therefore not merely a curious fact about astronomy. It is a warning about intuition. Our brains evolved to understand objects moving through space. A stone flies from one place to another. Smoke expands from a fire. An explosion has a center because fragments travel outward through an environment that already exists. Cosmic expansion does not have to behave that way. Imagine an ancient observer seeing galaxies recede and insisting there must be a central blast site somewhere. The mistake would not be in the observation. The galaxies really are separating on large scales. The mistake would be in assuming that familiar everyday geometry must explain the phenomenon. General relativity offers a different possibility. The metric itself evolves. Even the phrase, galaxies moving away, can be misleading at enormous scales. In cosmology, recession due to expansion is described through changing distances in curved dynamical spacetime. It cannot always be treated as ordinary motion through static space. This is why sufficiently distant galaxies can have recession rates greater than the speed of light without violating special relativity. No nearby object locally outruns a light beam. Instead, the cosmological distance between widely separated regions can grow according to the geometry of expanding spacetime. Again, reality refuses to fit inside the mental picture we inherited from daily life. And there is another revelation hidden inside this. If no galaxy occupies the center, then the Milky Way is not expanding away from some cosmic origin. Neither is Andromeda. In fact, Andromeda is gravitationally bound to the Milky Way and is approaching us despite the overall expansion of the universe. Stars inside galaxies do not simply swell apart with cosmic expansion. Neither do planets, people, or atoms. Local forces and gravitational binding dominate on those scales. Cosmic expansion emerges clearly across sufficiently large distances. So there is no universal image in which every object is being pulled outward from one special point. There is only a changing large-scale relationship between regions of space. Now reverse the movie once more. Galaxies approach one another. The universe becomes denser. Radiation becomes hotter. Atomic nuclei break apart. Eventually, our tested descriptions enter regimes of increasingly extreme energy. If we mathematically extrapolate classical general relativity far enough backward, we encounter a singularity, a point where the theory itself ceases to provide an ordinary physical description. But physicists do not generally interpret that singularity as a tiny physical dot sitting in some larger room. A singularity in the equations is often a warning that the theory has reached its limit. Quantum gravity should become important. String theory, one of Susskind's central fields, is among the major attempts to describe gravity consistently in quantum terms. Other approaches exist as well. No experimentally confirmed theory currently tells us exactly what happened at the earliest conceivable moment. So when someone asks, what was before the Big Bang? Or what did the universe expand into? Physics must be careful. Some cosmological models speculate about earlier phases, bounces, eternal inflation, quantum creation, or other structures. These remain theoretical possibilities, not established historical facts. The hot Big Bang model is extraordinarily successful at describing the evolution of the observable universe from an early hot dense state onward. It does not by itself give us a complete experimentally verified account of an absolute beginning. And that uncertainty matters, because perhaps the most profound lesson is not simply that we have failed to locate the universe's center. It is that a center may never have existed. For centuries, humans kept asking where we were located within a cosmic structure. First, Earth was the center. Then the sun became one star. The Milky Way became one galaxy. Our galaxy became one member of an enormous cosmic web. But modern physics changes the question itself. There may be no privileged place from which reality unfolds. Every observer carries an observable universe around them, defined by the history of light that can reach their location. Every distant civilization, if one exists, may look outward and see ancient radiation surrounding it. It may map galaxies receding in every direction. It may wonder for a brief moment whether it occupies the center of creation. And then its physicists may discover the same disturbing truth. The symmetry is not evidence of privilege. It is evidence that there may be no privileged place at all. Yet Susskind's world of black holes, holography, quantum information, and emergent spacetime hints that even this may not be the end of the story. Perhaps where is not among the deepest questions nature allows us to ask. Perhaps location emerges only after a more fundamental web of quantum relationships organizes itself into something we experience as space. If that is true, then the universe has not merely hidden its center from us. It may have removed the concept entirely. And somewhere beyond our observable horizon, beyond the oldest light we can receive, the cosmos continues into territory we cannot currently see. Maybe endlessly, maybe through a finite geometry that closes on itself, maybe as part of a structure our present theories only partially describe. There is no known sign pointing back toward a cosmic middle, no ancient crater where creation occurred, no throne at the center of space, only observers, each surrounded by their own horizon, each looking outward into the same expanding mystery. And perhaps the deepest question is no longer, where is the center of the universe? Perhaps it is this: if space itself is something that emerged from a deeper quantum reality, what would the word center have meant before space existed at all?